In the last module towards the end, we saw that of course nt goes to infinity as t goes to infinity with probability 1, but we were also able to show that nt over t goes to 1 over mu, where mu is the expectation of common expectation of the interarrival times. So of course, since nt goes to infinity, expectation of nt also goes to infinity. That's by monotone convergence theorem, which means that mt goes to infinity because mt is just the notation for expectation of nt. But from the fact that nt over t goes to 1 over mu, can we say that expectation of nt over t also goes to 1 over mu? That's not obvious. So what we are going to show is that is indeed the case, and that's what is called the elementary renewal theorem, whereby we show that mt over t indeed goes to 1 over mu. So that's a theorem which is a state, not proof. Just mention that the proof of the theorem uses a very important result called Wald's lemma, which has a wide variety of applications, not just here but in many other contexts in probability statistics and stochastic processes. So we'll just state Wald's lemma, and then we move on to stating without proof two most important theorems in the theory of renewal processes, known as Blackwell's theorem and key renewal theorem, and move on with that. So we start with what is called the elementary renewal theorem. So recall the renewal function, which was defined as mt, expected value of nt. We showed that this is finite. Since nt goes to infinity with probability 1, one can conclude by what is called the monotone convergence theorem that mt goes to infinity as t goes to infinity. So essentially, since nt increases to infinity non-negative with probability 1, expected value of nt by monotone convergence theorem also goes to infinity as t goes to infinity. That's okay. But we have also seen that nt over t goes to 1 over mu with probability 1 as t goes to infinity. What about mt? Do we have mt over t which is equal to e of nt over t also going to 1 over mu as t goes to infinity? Well, that's not immediate, because here we can't interchange expectation and limit. So this is where we want to state our first result, which is elementary renewal theorem, which says that this is indeed the case. So elementary renewal theorem says that mt over t indeed goes to 1 over mu as t goes to infinity. Now proof of this is not too difficult but a bit technical, so I'm going to omit that proof. But important thing to mention is that it uses a very important result of probability known as Wald's lemma. I'm going to explain what Wald's lemma is all about. But using Wald's lemma, elementary renewal theorem, namely mt over t going to 1 over mu as t goes to infinity, is proved by proving two things. So the proof is based on two parts, split in two parts. One part, one shows that limit of mt over t is greater than or equal to 1 over mu. That's one part. That's slightly easier. A slightly more complicated part is showing that lim sup of mt over t is less than or equal to 1 over mu. And at some stage, the proofs of these use what is known as Wald's lemma, which in its own right is an important result, and I'll explain what that result is. So what is Wald's lemma? Well, here's the motivation. If we know that yn, n greater than or equal to 1, is a sequence of independent and identically distributed random variables with finite common mean mu, then for any n greater than or equal to 1, if I look at the partial sum, which is Sn, y1 plus y2 plus yn, that also has finite mean, which is given by expected value of Sn is n times mu. So if each of them has mean mu, finite mean mu, then when you add n many of those, that has mean n times mu. So that's trivial. It's just additivity property of expectation. The question is, does the same result hold for a sum of a random number of the y's? So in Sn, we are adding n many y's, fixed number. But if we added a random number of the yi, is it true? So what do we mean by that? Let's be precise. Suppose tau is a random variable taking values in 1, 2, 3, etc., etc. So it takes positive integer values, but it's random, it's not fixed. And suppose we now consider what can be called S tau, which is y1 plus y2 plus etc. y tau. So each y is random, and the number of y's that we are adding is also random. So do we have a similar result for E of S tau? Well, the answer is not true in general. Needs a condition on the tau, the random variable tau, which gives you the number of terms that you want to add. So this is where Wald's lemma comes into play, and Wald's lemma gives you precisely the condition on tau under which an appropriate result for S tau holds. So suppose yn is a sequence of independent and identically distributed random variables with finite common mean mu, and suppose tau is a random variable taking values in 1, 2, 3, etc. with having finite expectations, so E tau is finite. Now comes the main condition, such that if you look at the event tau equal to n, that's an event because tau is a random variable, so that is an event. That event should be independent of yn plus 1, yn plus 2, etc., etc. for all n greater than or equal to 1. This would happen, just to give you an idea, this would happen, for example, if the event tau equal to n depends only on y1, y2, yn. It may not, but suppose the random time tau is defined in such a way that the event tau equal to n is a function of y1, y2, yn. That will certainly mean that this hypothesis condition is satisfied. That is, a event tau equal to n will be independent of yn plus 1, yn plus 2, etc. for all n greater than or equal to 1. Of course, this would also be true in another case when tau is completely independent of the whole sequence y. Anyway, so if tau satisfies this property, then the result is true. What result? That if you look at S tau to be the sum of tau many y's, then that has finite mean, and the mean is given by what it is expected to be, namely mean of the summands, common summands, and expected number of terms that you are adding times expected number of terms. Remember, where tau was fixed, deterministic, then it was mu into n. But of course now the number of terms is not fixed. That's also random. So you have to multiply mu by the expected number of terms. So that's exactly what this is. So that is what Wald's lemma is, and it's enormously useful in many contexts, and one of those is in proof of the elementary renewal theorem. Okay, now before we move any further and do any applications of renewal process, etc., etc., we are going to see two results for renewal process which are fundamental to everything that one does using renewal processes. So we have to state these results without proof, because the proofs are actually pretty complicated and quite long and highly technical in nature. So we'll state the results. These are two most important results on renewal processes. So we start first with a definition. So the definition is a non-negative random variable x is said to have a lattice distribution if there is a positive number d such that x takes values only in the set 0d, 2d, 3d, etc., etc. So there is a positive number d such that any value of x has to be a multiple of d. For example, any random variable taking non-negative integer values would be of this type, where d is 1. Now, for a lattice distribution, the largest such d is called the period of the distribution. Notice that if x has a lattice distribution which satisfies this property that it takes values only in multiples of d, then anything which is a divisor of d would also satisfy this condition, because any multiple of d is also a multiple of any divisor of d. So if you look at the largest such d, such that x takes values only in the set of multiples of d, then it's called the period of the distribution. Another thing to be noted is that we are not saying that x actually takes all these values. It may so happen that x takes values only 2d, 3d, and then 7d, and then 13d, and then 14d, and so on. So some values may be skipped. All we are saying is that if x takes any value, that has to be a multiple of d. Okay, anyway. So if f is the distribution of such a random variable, we say that f is a lattice distribution. Now, so this is just a definition. And when we state the results, you'll see the implication of this definition. So we'll have different results for lattice distribution and non-lattice distributions. Stopped? Okay. In what follows, f will denote the common distribution of the interarrival time of a renewal process, and mu will denote their common mean. We have already introduced these notations earlier. Note that if the common distribution f of the interarrival times of a renewal process has a lattice distribution with period d, then renewals can occur only at times t equal to nd, that is multiples of d. For example, we already saw that in order to show that nt has finite expectation, we constructed a new renewal process n hat t, wherein the interarrival times were allowed to take only two values, 0 and alpha, and so that was a lattice distribution with period alpha, and in that case we saw already this, that renewals could occur only at times which are multiples of alpha. So if the common distribution of interarrival times is a lattice distribution with period d, then renewals can occur only at such times which are multiples of d. Okay. So here are the results that I mentioned. As I said, we are only going to state this. So first one is called Blackwell's theorem. There are two parts of it. As I said, there will be different statements for lattice distributions and non-lattice distributions. So first part says that if f is not lattice, then for all a greater than or equal to 0, you look at the difference mt plus a minus mt. As t goes to infinity, this difference goes to a over mu. So this can be thought of, mt plus a minus mt can be thought of as the expected number of arrivals during the time interval open t to closed t plus a. So the length of this interval is kept fixed, and if you keep on shifting the interval to infinity, then this number, the expected number of arrivals happening during the interval t to t plus a, goes to a over mu. We'll try to argue why. We are not going to give a complete proof of this, but we'll argue why this is only natural. So this is the non-lattice case. What happens in the lattice case? If f is lattice with period d, then the result is slightly different. It says that the expected number of renewals at nd goes to d over mu as n goes to infinity. Now this is only natural to consider in case f is lattice with period d, because remember, when f is lattice with period d, renewals can happen only at times which are multiples of d. So if you take an interval, and if that interval does not contain any multiple of d, then of course such an interval expected number of renewals would be 0. So here of course you should only look at renewals happening at multiples of d. So this is only the natural thing to consider as opposed to what we consider in part A. Anyway, so this is Blackwell's theorem. The next result is what is called a key renewal theorem, which looks slightly complicated, but we'll try to explain what it is. And this is probably one of the most fundamental results when it comes to application of renewal process. So this result we only write for non-lattice distributions. So suppose f is not lattice, then for any non-negative, non-increasing function h on 0 to infinity, whose integral from 0 to infinity is finite, so h is a non-negative, non-increasing function. In particular, it could be strictly decreasing, but non-increasing would suffice, such that the total integral from 0 to infinity is finite. Then one has, if you look at the sum n equal to 1 to infinity 0 to t h t minus x d fn x, fn is the n-fold convolution of f. So Fn is the distribution of y1 plus x1 plus x2 plus xn, or distribution of Sn. So this converges to 1 over mu 0 to infinity ht dt as t goes to infinity. Now, it's not clear what is the interpretation of this, but as we go along, we'll understand what it really says. And of course, we'll see lots and lots of applications of this. Okay. So we have just stated two most fundamental, important and useful results in the theory of renewal processes. As I said, we won't prove them. Instead, we'll see some interesting applications. However, here are a couple of remarks which would sort of convince you why these results are kind of natural. So let's start with remark on Blackwell's theorem. So in the non-lattice case, the theorem says that the expected number of renewals during a time interval of length a, when that interval is taken to infinity, converges to a over mu. In other words, if you take such a time interval of length a far from the origin, then the expected number of renewals during that time interval is close to a over mu. Now, this is not so surprising. If you agree that as we go far away from the origin, the initial effects should wear away, if you agree that that is the case, and therefore, if you agree intuitively that this quantity should converge to a limit as t goes to infinity, then it's not so difficult to see why the limit must be a over mu. So let's see that. This limit obviously should depend on a. There's no doubt about that, because if you take a larger interval of larger length, this quantity is supposed to expect number of renewals in that larger interval is likely to be larger, etc. It should depend on a. So if you call this limit GA, then it's not difficult to see that G of a plus b equals G of a plus G of b. Because if you take an interval of length a plus b, you can always write it as a disjoint union of two consecutive intervals, one of length a, one of length b. So as the bigger interval goes to infinity, each of these two component intervals also go to infinity, and therefore you can easily see that G must satisfy G of a plus b equal to G of a plus G of b. And of course, it's also increasing in a, because if you increase the length of the interval, naturally the expected number of renewals increases. So G is an increasing function of a and satisfies G of a plus b equal to G of a plus G of b. And of course, one knows, that's a standard fact, that the only possible increasing solution of such equation must be that G of a is C times a for some constant c greater than or equal to 0. So only thing now we have to verify is, or sort of convince ourselves, is why is that c has to be 1 over mu. Well, that c has to be 1 over mu follows from the elementary renewal theorem. Why? Because first of all, c is g of 1 by the definition of c, which by definition of g of 1 is the limit as n goes to infinity of m of n minus m of n minus 1. But then the sequence of m of n minus m of n minus 1 as n goes to infinity goes to g1. So the average of the sequence, which is limit 1 over n summation k equal to 1 to n mk minus 1, should also have the same limit. But then if you look at the sum k equal to 1 to n of mk minus 1, that sandwiches to m of n minus m of 0 divided by n. So limit of that, of course, is 1 over mu. We already know that from elementary renewal theorem. So that establishes why c should be 1 over mu. Now the case when f is lattice, so we have just discussed the case when f is non-lattice. The case when f is lattice can be similarly explained. The thing to note here is that, as you already said, renewals can take place only at times t equal to nd. So the expected number of renewals in a time interval will not depend on the length of the interval. It will depend instead on the number of points of the type nd in that interval. So therefore, the limit of the kind of things that we are considering in the non-lattice case, limit t going to infinity mt plus a minus mt, cannot exist. Okay. Now let's give some remarks on the key renewal theorem. Not much to say. On the face of it, the theorem, as we already mentioned, looks quite intimidating, not at all as intuitive as Blackwell's theorem. However, the surprise is that even though it's not clear from the form of the theorem, it basically is nothing but a refined version of Blackwell's theorem. To be precise, in fact, key renewal theorem is equivalent to Blackwell's theorem, even though the form suggests that it's something completely different from Blackwell's theorem. I have no clue as to what they mean. However, it turns out that it's actually equivalent to Blackwell's theorem. By taking the function ht to be 1 if t is less than a greater than or equal to 0, and for t greater than or equal to a ht is 0, in the key renewal theorem, what you get is exactly Blackwell's theorem. You can convince yourself that. So, Blackwell's theorem follows from key renewal theorem by taking this particular function h, which is non-decreasing, non-negative, and has total integral finite. Conversely, if you assume Blackwell's theorem, how do you get the key renewal theorem? This can be obtained by simply approximating a general non-negative, non-decreasing h via step functions, which can be done. And for step functions, key renewal theorem is true. That's just Blackwell's theorem. Now, as it turns out, so this shows that the key renewal theorem is actually equivalent to Blackwell's theorem, although the form of the theorem doesn't suggest so. Now, as it turns out, I will see that key renewal theorem is perhaps the most useful result in applications of renewal processes in various contexts. And we'll see some of those applications. But before we get to that, here is, the crux of the matter as to why we could actually use key renewal theorem rests on this very useful simple lemma. Recall that S sub nt represents the time of the last renewal prior to the time t. Okay? Nt is the number of renewals up to and including time t. So S sub nt would represent the time of that renewal, the last renewal. In many applications, we will need to use the distribution of this random variable. Notice that by definition, Snt of course is non-negative, and by definition Snt has to be less than or equal to t, because it's the time of the last renewal prior to time t. So it has to be less than or equal to t. Now, as I said, in many applications we will be interested in really using the distribution of this random variable Snt. So this lemma gives you a formula for the distribution of Snt. So here is how it goes. This is the cumulative distribution function of Snt, probability Snt less than or equal to s. For any s between 0 and t, Snt has to be less than or equal to t. So for s bigger than t, this cumulative distribution function is 1. So what is its value between s and t, between 0 and t for any s? So probability Snt less than or equal to t, s, is first of all f bar t, which is the survival function, 1 minus ft, plus integral 0 to s f bar of t minus y dmy. Okay. So we are going to see why this lemma is true. Now, words on some notation. We have already introduced this, but just to recall, for a distribution function f, which here is the distribution, common distribution of the interarrival times, the associated survival function f bar is simply the function f bar x equal to 1 minus fx. So if x has distribution f, then f bar x simply represents the tail probability that x is greater than x. And secondly, in the lemma, you see that appearance of dmy. What is the meaning of that? Well, the meaning of dmy is it's just an abbreviation for summation n dfny. And it makes sense because after all, mx is summation n fnx. So dmy is just a notation for summation dfny. So there is no need to try to interpret this as integration with respect to m. Don't try to interpret that. Just think of this as a shorthand for this notation, summation n dfny. So when you integrate a function with respect to dmy, imagine that this is just a sum of integration of that function with respect to dfny summed over all n. So think of this as a shorthand for that. Okay. Now the proof of the lemma. So what did the lemma say? The lemma said that for any s between 0 and t, probability that Snt is less than or equal to s is f bar t plus that integral 0 to s, etc., etc. Okay, so here is the proof of the lemma. We start with probability Snt less than or equal to s. First of all, Snt less than or equal to s, we break up into what is the value of Nt. So Nt equal to s, Nt equal to n means that Sn is less than or equal to s and Sn plus 1 is greater than t. So remember, Nt equal to n means Sn must be less than or equal to t at Sn plus 1 must be greater than t. But if you are looking at an Sn, so we can write probability Snt less than or equal to s as summed over n equal to 1 to infinity. Firstly, Sn is less than or equal to t, Sn plus 1 greater than t, and Sn is less than or equal to s. But in the presence of Sn less than or equal to s, Sn is automatically less than or equal to t. So therefore, this is what remains. So anyway, for n equal to 0, S0 is anyway less than or equal to s. So for n equal to 0, the first condition that S0 is less than or equal to s is irrelevant. So it would simply say S1, s of 0 plus 1, which is S1 is greater than t. So for n equal to 0, the term is f bar t, and the remaining part is n equal to 1 to infinity, the same thing. Okay, let's carry on. So the first term is f bar t, and now summation n equal to 1 to infinity, probability that Sn is less than or equal to s, and Sn plus 1 is greater than t. So we condition on Sn. So let Sn be equal to y for some y between 0 and s. So what's the conditional probability that Sn plus 1 is greater than t given Sn equal to y? And then we integrate that with respect to the distribution of Sn, which is fn, dfny from 0 to s. But given Sn equal to y, probability that Sn plus 1 is greater than t is same as probability that Sn plus xn plus 1 greater than t. But given Sn equal to y, Sn is y, so probability that y plus xn plus 1 is greater than t. But now xn plus 1 is independent of Sn. So combining all of this integral simply purely becomes integral 0 to s, probability xn plus 1 is greater than t minus y, dfny, summation n equal to 1 to infinity. Of course, that gives you f bar t n equal to 1 plus summation n equal to 1 to infinity, integral 0 to s, f bar of t minus y, dfny. And now using the notation that summation over n equal to 1 to infinity dfny is exactly dmy, so you get this just notation. So therefore, we have proved the lemma. Now an intuition, notice that probability Snt equal to 0 is f bar t, because Snt equal to 0 means S1 is greater than t, which is same as x1 is greater than t, that is f bar t. And for s strictly positive and less than or equal to t, roughly dfSnts is f bar t minus s dms. Roughly you can think of it that way. So assume, for example, f is continuous with density f, in which case each fn also has a density, call it f, little fn. Then you can easily see that dms is indeed summation n equal to 1 to infinity fns ds. And what is it? It is approximately, roughly because density is not a probability, but roughly or approximately it's a sum of n equal to 1 to infinity probability of nth renewal occurring in interval s to s plus ds, and that is being summed over n equal to 1 to infinity. So that means that it's a probability that a renewal occurs in s to s plus ds. So the density of Snt on open 0 to open t is given by f Snt sds equal to or approximately equal to probability of a renewal in s to s plus ds, and the next interrival is t minus s, which is exactly f bar of t minus s dms. So this is just an intuition for this. So if I were to pinpoint the thrust of this particular module, it has to be, of course, elementary renewal theorem, which said that mt over t goes to 1 over mu. But more importantly, we stated what is known as Blackwell's theorem in the context of renewal processes, and key renewal theorem, which is the most fundamental result in the entire theory of renewal processes. And then we also saw that even though Blackwell's theorem is intuitively much more natural, the key renewal theorem is not at all so. It looks very intimidating, but nevertheless, I think we discussed that it turns out that the two theorems are actually equivalent in the sense that each one can be proved from the other. That Blackwell's theorem is a special case of key-renewal theorem, is easier to see, and then key-renewal theorem can also be obtained from this. So we are going to really apply these theorems, particularly the key-renewal theorem is going to be applied very, very heavily in all the applications of renewal theory. But in order to sort of advance those applications, we started with another very useful lemma, simple but useful lemma, wherein we actually found the distribution of what is to be called SNT, that is a time of the last renewal prior to time t. So that is something that the distribution of that random variable is something that would be used left and right in all applications of renewal processes.